So uh, let's talk about this aperture, circular aperture, and the resolution. Okay, so in this picture, if you see here, if your light passes through a small aperture, means it is a small hole like this. Okay, so we are passing the light. Say we are passing the single color light. Say this is a maybe the yellow color light, maybe, or we can use any color. So the point is, instead of a bright spot with the edge is sharp, we are not getting this part. So because of this diffraction phenomenon, okay, because of this diffraction phenomenon, we'll see that image is not sharp. Okay, so image in this case is not sharp, so we get the spot which is edge. We'll see this kind of here, this kind of fuzzy edge. Okay, this happens because of this diffraction phenomenon. Similar case we'll observe if we have two spots. Say for example, we have 2 point sources that are close to one another, produce overlapping image because of this diffraction. Okay, so for example, say for example, we have one slit over here, we have one slit over here. Say this shape is the circular shape. In that scenario, we are not getting the way this image is sharp. We are getting again this fuzzy image. Sometimes depending on the depending on the shape and size, this even though the two slits image looks like a single one. Okay, so this kind of defect we can observe in the case of because of this diffraction phenomenon. Okay, so there is a rule for that. If a circular aperture has a diameter d, then the first minimum will observed first minimum is the diffraction patterns occurs at theta equals 1.22. It is at 1.22 lambda over d. Okay, so d is the diameter of this aperture. So this is the d we are using here. D is the diameter of this aperture. So in this case, we are assuming that the aperture is large compared to the wavelength light. So we are assuming d is greater than lambda. Okay, so this equation theta equals, so by the way, theta will be measured in unit of radian. Okay, so theta will be measured radian. If this is the case, this condition to get the clear image we call the Rayleigh criterion. So this tells you that the diffraction limit to the resolution states that two images are just resolvable when the center of diffraction pattern of one is over the first minimum of the second one. So we are concerned about this part. Okay, and we'll come to later this point. This Heisenberg uncertainty principle also supports this idea. So we'll come to this point that the uncertainty in position times uncertainty in the momentum is greater than equal to h over 2 pi. Okay, so this means this is the uncertainty in position, and this is delta p is the uncertainty in momentum. The product must be greater than h over 2 pi, where h is called the Planck's constant. Okay, this is called the Planck's constant. So the Heisenberg uncertainty principle supports this concept. Okay, so this is the same picture. We just see that this is the position for the first minimum. So if this is the case, we can see the clear picture of object 1 and object 2 if this condition is satisfied. Okay. So this is the image of the photograph taken using the ground-based telescope and the Hubble Space Telescope. Okay. So based on that, we can move further and say that come to the topic is the diffraction, the X-ray diffraction. Okay. So this diffraction basically tells you that if we are passing the light in, instead of light, we are taking the X-ray because they have high frequency, and it has high frequency and comparatively low wavelength. And one important feature is that this wavelength is maybe comparable with the distance between atoms, distance between two planes. So basically, we are talking about planes. I'm saying that this is atomic plane. Okay, this is atomic plane. That's the reason we are using the X-ray. So this in this refraction, we are using the Bragg's law. The Bragg's law equation tells you that 2d sine theta equals m times lambda. So m is equal to 1, m could be 2, or m could be 3. Okay. So if we use m is equal to 1, then we'll get 2d sine theta. So we can say theta 1 equals lambda. So this is the condition for first order diffraction. Okay. If you put m is equal to 2, we have 2d sine theta 2 equals 2 lambda, which is the second order diffraction. Okay. So, but here be careful that the angle theta is not the angle of incidence. So the theta is general practice in geometrical optics is measured with respect to the surface itself. Okay. So let's go to find this equation. So in this picture, say I will draw two lines over here. So I say an n1 n1 is perpendicular to incident light. Okay, so you see here, this first incident light is going to be reflected from the first plane. Say I just put the name. Say it is, say just put some name. Say it is m a. I put m a prime. So if you look at this picture, we can say that m a gets reflected from a plane we can say from the top plane. Okay, the second ray, we can say m prime b gets reflected from say from the second plane. Okay, so even though we use the term reflection, this is not actually reflection. These are the diffraction phenomenon. Okay, this is not reflection. So you see that we have, it is, say m prime b will be reflected along b m, say I would say m double prime. Okay, it will be reflected just like this. So you see that we have two reflected rays. We have two reflected rays. You see from this picture, one is AM prime and second is B double prime. Okay, so if you consider from the beginning, we can say that we can say that the path difference of waves from first and second plane. Plane means we are talking about the atomic plane. Okay, if this is the case atomic plane, we can use the picture over here. So if you take the triangle AN1B in triangle A N1B, I take an angle sine theta. Sine theta will be equal to N1B over AB. So from the picture, you can say theta is the angle made by incident ray with atomic plane. Okay, is not the angle of incidence. So be careful, not angle of incidence. Okay, so and I can write here N1B equals AB times sine theta. So AB from the picture is the distance between two atomic plane, and two atomic plane you can see here. Okay, two atomic plane. So this atomic plane distance is d. So I'm going to replace that with d. So this will be d sine theta. Similarly, we can find say I draw the perpendicular AN2. So AN2 is perpendicular to the incident line, perpendicular to the reflected light from second plane. Okay, second plane. If this is the case, I will do the same math and we can find Bn2. I can find Bn2 or N2B is also equals d sine theta. So from this picture, we see that the path difference between the waves is basically this one, N1B plus Bn2. Okay, so the path difference, so you can find the path difference between the waves is path difference between the waves is N1B plus N2B, which equals 2d sine theta. Okay, so we know for constructive interference, we must have 2d sine theta, which is path difference, must be equal to integral multiple of lambda. Okay, so lambda here is the wavelength of light used. Okay, so we can use this equation to find to find the condition for the different order of the diffraction. Okay, so that's why we're talking about this part. And the plane, we also call it the uh, Bragg's plane. So the Bragg's plane is basically the plane between the two atomic planes. Okay, so let's move further. So if you understand up to this point, you can solve this problem, this practice problem. And this is just a picture to make a model how in the atom, different atoms forms the plane. So for example, this one is one atomic plane. We can consider this as the atomic plane. So the distance between two atoms is basically the distance between the two planes. Okay, so we are using this concept to find the interatomic distance between the atoms. And there are some resources we can use. You can use if you want to look at different concept in more detail. The one very useful may be this one, the lecture from the UCI open, and there are some link for the simulations. You can go over that. Okay,